This video is going to be about using NOR gates to build any circuit. So before you watch this video, just make sure you check out the one that I made about using NAND gates to build any circuit. So in this video, I'm going to explain how you can use NOR gates to build any AIO circuit. You can build any circuit at all, but in particular, I'm going to build an AIO circuit. By that I mean AND gates, that's the A part, OR gates, that's the O part, and inverter gates, AOI, inverter gates also known as NOT gates. So stay tuned and I'll explain how to do it. And before we get started, let me just jog your memory about what a NOR gate is. So a NOR gate is, of course, the opposite of an OR gate. And of course, down here, I could fill in the truth table for an OR gate. Of course, an OR gate has a 0 when both inputs are 0, but in every other case, if X or Y or both of them are 1s, I get a 1. So this is an OR gate, and a NOR gate is just the opposite. So I'm inverting this. So my 0 becomes a 1, and all my 1s becomes 0. So this Z here is my NOR output. All right. This is a very important slide here, so you might want to pause the video and copy this down. So here in this first case, I am using a NOR gate to create a NOT gate, right? So let's just say my input is X. Coming into here, I have two X's, of course, and coming out of this NOR gate, I have X ORed with X and a NOT over it. That's what a NOR gate does. It's an OR gate with a NOT over top of it. Of course, I can split this up using De Morgan's law, and that would give me a NOT X and NOT X, which you perhaps remember those basic rules. NOT X ANDed with NOT X is NOT X. So in this first case, I used one NOR gate to create a NOT gate. Not too bad. All right, so let's take a look at this next case. Now you already know that I'm using this as a NOT gate. So if this is X, coming out of here, I have NOT X. If this is Y, coming out of here, I would have NOT Y. And now I have another NOR gate, so that would be NOT X ORed with NOT Y with a NOT over it. Again, that's what a NOR gate does. It ORs it and then NOTs it. So I'm going to split this up using De Morgan's law. That gives me NOT X ANDed, right? Because when you split up a bar, you change the sign of an OR to an AND or an AND to an OR. And that's NOT Y, which of course is the same thing, right? If you have two NOTs over something, you can cross them out. This is the same thing as saying X ANDed with Y. So there we go. I have used three NOR gates, 1, 2, 3, to create an AND gate. In this last case, I'm going to use two NOR gates. So let's again call my input X and Y. Coming out of here, I would have X or Y NORed. And then this, of course, is really just a NOT gate. So I have X or Y not NOTed, which of course, I can cross these out. That's the same thing as X or Y. So there we go. I've used two NOR gates to create an OR gate. I've used three NOR gates to create an AND gate. And on top, I've used one NOR gate to create a NOT gate or an inverter gate. All right, stay tuned for the next slide. And here is my circuit from the first page. And you can see up top, I have created a circuit out of only NOR gates. Here I took the NOT gate and I replaced it with one NOR gate. Then I took the AND gate and replaced it with three NOR gates, just like I did on the previous slide. I took this AND gate, replaced it with three NOR gates. There we go. And I took this OR gate and replaced it with these two NOR gates. Got it? Doesn't look too bad. Now there's one more thing you can do, and you know this already. If you have two NOTs in a row, like if I have NOT X NOTed, that is the same thing as just X. So I'm going to look carefully to see if I have two NOT gates in a row. So I'm looking carefully. Now that is not a NOT gate, and that is a NOT gate. Remember, it's a NOT gate if you have one input going to both of the inputs of your NOR gate. So in this case, I have two inputs coming in. That's not a NOT gate. So somewhere I might have two NOT gates in a row. Excuse me. Oh, here we go. This is definitely a NOT gate, and that is going into another NOT gate. And I think that might be the only case where I have two NOT gates in a row. Of course, I can cross them both out. Again, if you have two NOT gates in a row, you must cross them both out. Now, that's the only case that I can see where that happens. So I can actually connect this wire all the way around to this wire and eliminate these two gates altogether. You can only eliminate pairs of NOT gates. That's the only thing you can eliminate. All right, now let's check out the last slide to look at the final simplified version. And here is the last slide. So you can see up top here, this is my original AOI circuit and or inverter circuit. Now, if I were to build this circuit, I would require one chip for my NOT gate, my inverter gate. I would require a chip for my AND gates, and I would require another chip for my OR gate. So this circuit would require 3 chips to build. All right, let's look at the circuit underneath. Now, of course, chips contain only one type of logic gate typically. So here I'm going to need a logic gate. Now, of course, you can contain a logic gate contains a chip contains 4 logic gates. So 1, 2, 3, 4 logic gates on one chip, and 1, 2, 3. I'm going to need a second chip for these 3. And I think I can build this circuit below here. Well, as a matter of fact, I'm sure I can build it below using only 2 chips. So there you go. I've actually decreased the number of chips required to build this circuit below. And again, if I'm building a million circuits for washing machines or whatever, I can actually save money using only one type of gate. All right.